Welcome to my YouTube channel. In physics, experiments are very important because they bridge the gap between theory and reality. They provide hands-on experience to deepen understanding. The quote emphasizes the importance of empirical evidence and the scientific method. It highlights that a scientific theory, regardless of how elegant or well-reasoned it may seem, must be validated by experimental results to be considered correct. In this particular experiment, we are supposed to convert a given galvanometer of known resistance and figure of merit into an ammeter of a given range, and we will verify the same, right? So, in order to convert a galvanometer into an ammeter, a very low resistance wire, which we call as shunt, it is to be connected in parallel to the given galvanometer. So suppose this is the galvanometer. Galvanometer, as you are aware, it's an electric device which is used to detect the current, right? It doesn't measure current, it is used to detect the current. This is a galvanometer. And suppose this galvanometer shows full-scale deflection when current Ig is made to pass through it. So maximum safe value of current that can be made to pass through this galvanometer is Ig. So in order to convert this galvanometer into an ammeter, what we need to do is we need to convert, or rather we need to connect a low value of resistance, extremely small value of resistance, which we call as shunt. It will be represented by capital letter S. So this low value of resistance shunt is to be connected in parallel to the given galvanometer. Suppose this has been converted into an ammeter of range 0 to 3 ampere. I is 3. So this is the current I. And this parallel grouping, the parallel grouping of this galvanometer and this low value of shunt, this constitutes an ammeter. So this will become an ammeter. So this ammeter is having a range of 0 to 3 ampere. So this I is 3 ampere over here, right? Now students, the value of shunt S is to be adjusted in such a manner that out of total current I, only Ig current flows through the galvanometer, and rest of the current, that is I minus Ig, flows through the shunt, right? So these two are connected in parallel. Therefore, potential difference across the galvanometer would naturally be equal to the potential difference across the shunt. So the current flowing through the galvanometer is Ig, and capital G, that's considered to be the resistance of the galvanometer. So PD would be Ig multiplied by capital G. And potential difference across the shunt is current flowing through the shunt is I minus Ig multiplied by shunt value, that is capital S. So students, the value of shunt, which is to be connected in parallel to the given galvanometer so as to convert it into an ammeter of a given range, is Igg divided by I minus Ig. So this is the working formula, right? So the length of the wire of radius R having a resistance S is calculated from this value. It is, we are aware resistance, it's directly proportional to length of the wire and inversely proportional cross-section area. So rho L by A. So it can be written as rho L, cross-section area is pi R square. This is a wire which we will be using as a shunt, right? This is a wire. Suppose its radius is R and the length is L, and the resistivity of its material is rho, and its value is S. So obviously it would be rho L by A. That is what I've written over here. A is the cross-section area, which is pi R square. R in terms of diameter can be written as D by 2. So it would be D square by 4. So students, length of the wire which is required so as to be connected in parallel to this given galvanometer, it would be S pi D square divided by 4 times resistivity. Now look, S is the value of shunt which we can obtain from this particular mathematical formula, right? Capital D is the diameter of the wire. Normally we make use of constantan or manganese as a standard resistance wire. So D is the diameter of that wire, which we can find by using a screw gauge. And rho is the resistivity of the material of the wire. it is known to us. The resistivity of manganese or constant 10, that will be known to us, right? So from this, we can easily calculate the value of the length of the constant 10 or the manganese wire that is to be used as a shunt to be connected in parallel to this galvanometer. Now let us find out the galvanometer resistance and the figure of merit of the given galvanometer. A galvanometer is a device used to detect small electric current in a circuit. It has a moderate resistance and has a very small current carrying capacity. The resistance of a galvanometer can be found by using half deflection method. The circuit diagram for this method is as shown. First and foremost, key K1 is inserted while key K2 is open, and deflection theta is determined with a suitable value of resistance. Now let us take the first reading. As we are aware that a source of EMF is required, so we are applying an EMF of 2 volt, and we are introducing a resistance of 4000 ohm from the resistance box R. We need to ensure that key K2 is open while key K1 is closed. Now you can check the deflection in the galvanometer. It is showing a deflection of 20 divisions. Now we need to insert key K2 also. And without changing the value of capital R, we need to adjust the value of capital S, that is the resistance from the another resistance box. By taking out the shunt resistance S equals to 70 ohm, we can easily check that the deflection in the galvanometer is 10 divisions. Now let's concentrate on the second reading. Here again, the EMF is considered to be 2 volt, that is same as was in the first reading. And again, key K2 it should be open while key K1 should be closed. Now taking a total resistance of 5500 ohm, we need to see the deflection in the galvanometer, which is 15 divisions. Now we will repeat this step. Again, the key K2 is closed and the value of shunt resistance S is to be adjusted in such a manner that the deflection in the galvanometer reduces to exactly half the value obtained in the previous step. That is, we need to obtain a deflection of 7.5 divisions. So for that, we can easily check that the shunt resistance is to be 73 ohm. As you can notice, now the deflection in the galvanometer is 7.5 divisions. Now for the final and the third reading, we need to repeat the above steps. Key K2 is open while key K1 remain closed. We need to change the value of capital R and note the galvanometer deflection again. So in this case, if we apply a resistance of 8500 ohm, then the deflection obtained in the galvanometer is found to be 10 divisions. Now in the very next step, key K2 is inserted and the resistance from the shunt resistance box is so adjusted that the deflection in the galvanometer becomes 5 division. So we can see for S equals to 74 ohm, the deflection is 5 divisions. This is the observation table where I have noted down all the readings obtained during the experiment so as to calculate the galvanometer resistance as well as the figure of merit. So students, now let's complete these observations. The resistance of the galvanometer, which we have determined to be 73.28 ohm. This is the value of capital G, which is the resistance of the given galvanometer. Figure of merit, as you are aware, it is the current which is required to produce 1 division deflection in the galvanometer, and it is also found to be 2.39 into 10 raised to the power minus 5 ampere per division, right? Number of divisions in the galvanometer which I am making use of, it is 30. So the current for which the galvanometer shows full scale deflection, it would naturally be total number of divisions in the galvanometer multiplied by the current required to produce one division deflection in the galvanometer, which we call as figure of merit. So it will be Ig would be equal to N multiplied by K. So this is 30 multiplied by 2.39 into 10 raised to minus 5. So that comes out to be 7.17 into 10 raised to power minus 4 ampere. So this is the safe value of current which needs to be passed through the galvanometer. This is the current for which the galvanometer will show maximum deflection, right? Now this galvanometer is to be converted into an ammeter of range 0 to 3 ampere. So over here range of the ammeter, that is 3 ampere. So students, substituting the value of capital G, Ig over here, the value of shunt can be easily calculated. So let's substitute this value, that is 7.17 into 10 raised to power minus 4 multiplied by G, galvanometer resistance, that is 73.28 divided by I minus Ig. I is the range which is 3 minus 7.17 into 10 raised to power minus 4. So students, if you solve it, the numerator, that will give you about 525.4 multiplied by 10 raised to power minus 4. 73.28 multiplied by 7.17, that will give you 525.4 divided by this term. This is negligible as compared to 3. So 3 minus this term, it can be considered to be 3 only. This term can be neglected as it's too small as compared to 3. So this comes out to be 175.1392 into 10 raised to minus 4. Right? So approximately it can be considered to be 0.0175 ohm. So as I've told you, shunt is a very low resistance wire, right? So the value of S, it comes out to be 0.0175 ohm. This wire of low resistance is to be connected in parallel to this given galvanometer. And the length of the wire, so as to obtain this value of shunt resistance, is given by this particular formula, right? The value of shunt is obtained to be 0.0175 ohm, right? Now we will make use of a Constantin wire. Now you are aware, students, for a standard resistance wire, it must possess two properties. It must have high value of resistivity and it should have low temperature coefficient. So we will make use of Constantin wire. Constantin is an alloy consisting of 60% copper and 40% nickel. So for Constantin, the resistivity is found to be, it's a constant value. It depends upon the nature of material of the wire. So resistivity of Constantin, it can be obtained through a table which is provided in every lab manual. So it is 4.8 into 10 raised to power minus 7. SI unit of resistivity is ohm meter. So this is a value which we are aware of, right? This is the standard value of the specific resistance or the resistivity of Constantin wire. Also, the diameter of this wire, it can be easily determined using a screw gauge, right? So corresponding the SWG, standard wire gauge number 18 of a Constantin wire, the diameter is obtained to be 1.2 millimeter. This, as I've told you, can be easily determined using a screw gauge. So in SI, it would be 1.2 into 10 raised to power minus 3 meter, right? So the value of D is obtained, the value of rho is known to us, S is known to us, the length can be easily calculated. So let's calculate the length of the shunt wire to be used. So S is 0.0175. The value of pi, it can be considered to be 3.14. Diameter, that's found to be 1.2 into 10 to the power minus 3 and divided by 4 times the resistivity, which is 4.8 into 10 raised to the power minus 7. So students, after solving this value, what we get is 0.079 multiplied by 10 raised to the minus 6, 10 raised to the minus 3 to the power 2, we'll get 10 raised to the minus 6. 1.2 square, it will be 1.44 multiplied by 3.14 into 0.0175, that comes out to be 0.079, right? Divided by the denominator, that will give you 19.2 multiplied by 10 raised to the minus 7. So it is 0.79 divided by 19.2, 10 raised to minus 7. So it will be 10 raised to the power plus 7 minus 6, 10, and 0.079 multiplied by 10, that will give you 0.79. So this comes out to be 0.041. It will be in meter, right? So the length of this shunt wire, which we need to be using, is 4.1 centimeter. So this length of the Constantin standard resistance wire of SWG number 18, having diameter of Itna, is to be connected in parallel to the given galvanometer, right? So as to convert it into an ammeter. Now students, this is the circuit diagram for the verification, right? This is the source of EMF. This is the converted ammeter, right? This is the low value of resistance wire, shunt, whose value is determined to be 0.0175 ohm. So this wire needs to be connected in parallel to this galvanometer, so as to convert it into an ammeter, right? This is the ammeter. So we need to verify this. The reading shown by this actual ammeter and this converted ammeter, they must be same. And this is the rheostat, so as to change the value of current through the circuit elements, right? So this is the circuit diagram. So for verification, we need to connect the battery, rheostat, a key in series with an ammeter and this converted ammeter, right? We need to take the reading of the ammeter and the corresponding number of division in the galvanometer. And then we can find out the current by multiplying the magnitude of each division with the number of divisions. So that is how we are going to verify it. A galvanometer can be converted into an ammeter by connecting a low resistance in parallel to it, which is called a shunt resistance. And in order to achieve it, the connections are to be made as per the given circuit diagram. This is the shunt, which we need to connect it in parallel to the given galvanometer. And this is the formula to obtain the value of shunt resistance. Take the reading of the ammeter and of the corresponding number of division in the galvanometer. We need to find the current by multiplying the magnitude of each division with the number of divisions. This is how the verification is done. Now in the second reading, you can easily check the ammeter reads a current of 1 ampere. Correspondingly, the galvanometer shows a deflection of 10 divisions. For the final reading, the ammeter shows a current of 1.5 ampere and correspondingly, the deflection in the galvanometer is 15 and thus the reading of the converted galvanometer is 1.5 ampere. So students, this is the observation table. The range of the converted ammeter, that's 3 ampere. Number of divisions of the galvanometer, that's 30. So basically one division of galvanometer would be 3 divided by 30. That is, one division of galvanometer will show a reading of 0.1 ampere, right? So as we have observed these values, let us note this down on this particular observation table. In the first case, we will change the value of rheostat, resistance values. So accordingly, different values of current can be obtained. So corresponding to an ammeter reading of 0.5 ampere, we can observe that the galvanometer shows a deflection of 5. So I dash, it would be equal to 5 multiplied by 1 division of galvanometer, that is 0.1 ampere. So it comes out to be 0.5. So the converted ammeter and the actual ammeter both shows the same reading. So there is no difference at all. So first observation is verified. Similarly, in the second case, corresponding to 1 ampere, we get a deflection of 10 divisions in the galvanometer. So the reading in the converted ammeter is actually 10 into 0.1. So it will be 1 ampere. So again, this reading has also been verified, right? So the difference comes out to be 0. And in the final reading, what we have observed is corresponding to an ammeter reading of 1.5 ampere, the galvanometer shows a deflection of 15 divisions, which is equivalent to a current of, again, 1.5 ampere. So as we can check that the converted ammeter and the actual ammeter both shows the same reading. So the result has been verified. That is, the given galvanometer has been converted into an ammeter of a given range. So students, let's conclude this particular experiment and keep performing experiments, keep performing activities in your respective physics lab and try to clear the concepts involved, right? So keep watching my videos and please do recommend my videos to your friends and colleagues. Thank you.